me le due. Maccaro Mikado, la put put cade, il a ravioli. Poti la caprenan de motis. Patachou, le pona con la serpeta.
What are nanoparticles? Do they exist? What do they look like? Why are they important?
Nanoparticles are small groups of atoms, usually metals or metalloids, stabilized by a ligand shell. Ligand is a molecule that binds metals. In the case of nanoparticles, ligands are usually small organic molecules. Nanoparticles exist at the nanoscale, which is between 1 and 100 nanometers. Due to size and surface energy interaction, nanoparticles have properties that differ from those of the bulk. The physical and chemical properties of nanoparticles can change due to variations in size, shape, and surface, as well as in composition.
Nanoparticles have many biological applications, specifically medical imaging, treatments, and gene therapy. Many biological processes, particularly on the cellular level, exist at the nanoscale. Thus, it is useful to have technologies that can be used to influence the cellular environment. Due to their small size in relation to wavelengths of visible light, nanoparticles exhibit a unique optical phenomenon called a localized surface plasmon resonance. An LSPR occurs when the wavelength of incident light is at the same frequency as the oscillating electrons in the conduction band of the metal. Since the frequency of light is resonant with the oscillating electrons, the electrons can absorb light, increasing the amplitude of their oscillation, producing a plasmon. This can be modeled by the Drude model. LSPR causes a localized electric field and enhances light, which leads to optical and electrical applications. Surface-enhanced Raman scattering is a spectroscopic technique that utilizes LSPR to enhance Raman scattering for better imaging. LSPR also has applications in enhancing LEDs and in photovoltaics.
We looked at the molecular orbital energies of gold and silver nanoparticles of various sizes. We care about molecular orbital energies because oxidation relates directly to HOMO energy level, which can be functionalized for catalytic applications. Selective oxidation of hydrocarbons by air molecular oxygen is a significant process in the chemical industry and provides a greener route for the synthesis of some fine chemicals and intermediates. The aerobic oxidation of hydrocarbons is an important commercial process for oxygen-containing compounds such as alcohols, aldehydes, ketones, carboxylic acids, and epoxides. However, the reaction conditions are often harsh. The reagent mixtures are corrosive, and the reactions are frequently unselective. They also generate environmentally hazardous waste and byproducts. Generally, low selectivities are observed in oxidation reactions, which can be related to the formation of undesired products due to easy overoxidation of carbonyls and alcohols. In avoiding such overoxidation, conversions are often low, which is a serious disadvantage.
Nanomaterial-based catalysts are usually heterogeneous catalysts broken up into metal nanoparticles in order to speed up catalytic process. Metal nanoparticles have a higher surface area, so there is increased catalytic activity because more catalytic reactions can occur at the same time. Nanoparticle catalysts can also be easily separated and recycled with more retention of catalytic activity than their bulk counterparts. These catalysts can play two different roles in catalytic processes. They can be the site of catalysis, or they can act as a support for catalytic processes. When the word nanoparticle comes to mind, many people think of spherical objects. However, under close examination, it can be seen that many nanoparticles are not in fact perfect spheres. We wanted to compare the particle in a sphere energy calculations to see if it is an accurate model for nanoparticles, despite their non-spherical shape. In order to accurately calculate the energies of the molecular orbitals, we had to first optimize the geometry of the nanoparticles.
This was done by finding the charge and spin state with the most stable or lowest energy configuration. These and all other computational calculations were carried out using WebMO and the MOPAC semi-empirical program with a PM6 theory. The spin state of the molecule depends on how many unpaired electrons are present. A singlet spin state occurs when there are no unpaired electrons, a double when there is one, and a triple when there are two. All the nanoparticles we looked at had either doublet or singlet spin states, depending on their charge. Finding the optimal geometry of the nanoparticles consisted of testing different charges and spin states and looking for the one with the lowest total energy. Although typically thought of as neutral, we found that the nanoparticles were most stable with a charge. Once the most optimal configuration was found, molecular orbital calculations were able to be done.
We calculated the molecular orbital energy levels of the most stable spin state for gold and silver nanoparticles using the particle in a sphere model. The particle in a sphere assumes that the particle can move anywhere on the surface of a sphere. The energy of the particle in a sphere is delta E is equal to h bar squared over moment of inertia times L times the quantity of L plus 1. The radius of the nanoparticles was determined using WebMO. Since the nanoparticles are not spheres, two different distance measurements were used to compare to see if there were any similarities or differences. Based on the calculations, it is evident that the energy and radius had an inverse relationship. So as radius increased, the energy decreased. For example, gold-15 had a molecular orbital energy of 5.2 times 10 to the negative third electron volts, and it decreased to 2.6 times 10 to the negative 3 electron volts as the radius increased. We also calculated energy for gold-35, silver-15, and silver-35. The molecular orbital energy for silver was slightly higher than those of the gold particles. Additionally, the energy of particle in a sphere was then compared to the most stable molecular orbital energy using WebMO. We found the HOMO, LUMO, and in some cases SOMO energies for the particles. The particle in a sphere model most closely corresponded with the LUMO energies of WebMO. Although WebMO was about 3 orders of magnitude larger than the particle in a sphere, we can see that they both show a trend in value as the radius increased or decreased. The reason behind these results could be that the calculation by hand was assuming the nanoparticles were perfectly spherical, when in reality they are more complex than a sphere shape. Thus, using the WebMO gives a more accurate result because it takes into account the unique shape of the nanoparticles.
Then we wanted to see the shape of orbitals of the nanoparticles. Looking at the pictures, do you think they look like s orbital, p orbital? What about a d or f orbital? Do any of the nanoparticles look like a particle in a box wave function? No, because it's not oscillating and it's not wavy. It seems like none fits to the description and that nanoparticles are more complicated than the simple models.
So what did we learn? Simply put, we learned that nanoparticles are more complicated than a simple particle in a sphere or particle in a box wave function. Based on our energy calculations, we found that although the nanoparticles demonstrate similar trend in change in energy as particle in a sphere, the two are not interchangeable due to the high differences in energy values. As we mentioned in the beginning, there are numerous applications that utilize the molecular orbital energies of nanoparticles.